Thank you, Tom, for the nice introduction and for the invitation here. So all of this is joint work with Yu Deng, Andrea Naud, and Hetien Yue, and Andrea, I think, is also joining us online. Okay, so we have a pretty mixed audience. With some mathematical physicists, we get analysts and other fields. So I tried my best to make this accessible, and we'll spend the first 10 minutes just talking about ODEs, right? And this will be rather slow paced, but it introduces some of the concepts that we'll hear about, right? And then I'll tell you about our result, put it into historical context, and the last 20 minutes or so of this talk will be about the proof, right? But at a very high level. Okay, so let's start with this slow paced introduction. So some of you have already seen this kind of diagram in my short talk about half a year ago. And this is what you could think of here, the harmonic or nonlinear oscillator, right? So this kind of physical system can be modeled using the following evolution equation, which you just obtained from Newton's second law, right? So here on the right-hand side, we have this derivative of a potential energy. And this is here, where I have to make some modeling assumptions, right? What is this potential energy going to be? And throughout this talk, I will always focus on this particular case right here, where it will take a quadratic quartic flow, right? So it will have one quadratic term, which is u squared over 2. And it will have potentially one quartic term, which is u to the 4 over 4. And here I'm allowing some prefactor lambda, right? So that's a fixed constant. It will always be non-negative. So this makes a nice coercive quantity and will be non-negative. But I'm allowing it to be 0, right? So it could be that this term is not there. In that case, I would just get a linear equation, which would be the harmonic oscillator. But if it's non-zero, I would get a cubic term as well. Now, this slide is titled Hamiltonian equations. So let's define the Hamiltonian. Right. So the Hamiltonian is a function from R2 into R, depends on two variables, Q and P. Think of Q as a position and P as a momentum, right? And it has this potential energy that we had before, and an additional quartic term in the momentum, which corresponds to the kinetic energy. Now, using this Hamiltonian, I can rewrite my equation here as follows. So first, I introduce new variables. So Q will now become U, and P will become the time derivative of U. Right? And then this kind of equation can be written as follows. So the time derivative of Q is just P. That's just so that my change of variables remains consistent over time, right? And then the actual equation is encoded into the second component right here. Right? Now, you stare at this for a little bit, and then what you realize is that you can also write this in terms of the Hamiltonian. Right, so this first component here is the P derivative of H, and the second component is minus the Q derivative of H. And whenever you have something that looks like this is what's called a Hamiltonian ODE. Right? So Hamiltonian ODEs have lots and lots of nice properties, but the properties that we care about today will all be associated with the Gibbs measure. So let me define this particular Gibbs measure first. So I will always denote it by mu. It will for now be a measure on R2, right? So it will be a measure in Q and P. And it consists of 3 separate parts. So one thing here is this normalization constant. This just turns this into a probability measure, right? So this kind of normalization is very important in statistical mechanics, but for us doesn't matter so much. Then I have this exponential factor here containing the negative of the Hamiltonian, and I have the Lebesgue measure in both Q and P, right? And at least for the potential energies that we care about, it's clear this is a nice, well-defined probability measure. Right, so I can take my form of the potential energy and I can insert it here, right? And then the only thing that I also did is I factored the exponential in 2 separate terms, right? So one term has the quartic one and one term has the quadratic ones.
You don't have an energy, like a coupling before the H in the definition?
Right, so there could be a beta, which would be the inverse temperature. Here I'm just setting this equal to 1. Good question. So, so this is what we would get here, right? So the inverse temperature has been set to 1. Now I'm still allowing this kind of lambda to be 0, right? In this particular case, this factor here would just be constant, right? And then I would actually get a Gaussian measure, right? A very good friend from probability theory. Right? If lambda is positive, then this will of course no longer be constant, but it will still be bounded by a constant, right? Because lambda is positive and Q to the 4 is non-negative. So even though the measure is no longer Gaussian, it will still be absolutely continuous with respect to the Gaussian, right? So one kind of teaser already, this kind of absolute continuity can actually fail when we look at PD analogs of this, right? So it's just a teaser for now. Okay. So why do we care about this measure, right? We care about the
PDE setting. You mean that you're going to a more than R2?
Yeah, well, an infinite dimensional space, but we'll get to this in time. So here's just this measure that we had, and here's the theorem that will motivate the rest of this talk. I'll just call it invariance, and it tells you that this Gibbs measure mu is invariant under the Hamiltonian flow. Right. So let me put this in slightly different words because it might be more helpful to some of you. Right. It tells you the following. Right. So let's assume that our Q0 and P0 are random. Right. It's not just a fixed vector; it's a random vector. And it's assumed that the law of this random vector is given by the Gibbs measure. And that makes sense because it's a probability measure. Right? If that kind of assumption is satisfied for your initial data, then this theorem tells you that the law of the solution, so law of Qt and Pt, will still be given by the Gibbs measure for every time t. Right? So this law does not change in time, it always remains the Gibbs measure, and this is why we call it invariance.
When you say the change in time is by assumption solving the Hamiltonian.
Yes. So Qt and Pt are the solution to the Hamiltonian ODE. Exactly. Okay, so what would be the proof of this? This is something that I can actually sketch for you here. The proof is essentially two different steps. One ingredient is the conservation of energy, and this will tell you that the Hamiltonian is actually constant along the orbit. Right, so it's constant along the solution. And then the second ingredient would be Liouville's theorem for divergence-free vector fields. So it turns out whenever you have a Hamiltonian vector field, it's always divergence-free. And then Liouville's theorem tells you that the corresponding flow preserves the Lebesgue measure. And you put these two things together and you get the theorem. Okay. So there's a slightly different setting where we have a similar result. And this setting concerns Langevin equations. Okay, so here we will no longer be talking about ODEs, but we will be talking about SDs. Okay, so this is a stochastic differential equation. The e to the differential of q, which is my position variable, is given by minus v prime of q dt. And that's just a classical term, a drift term. And then we have the stochastic forcing here, which is square root of 2, that's just the normalization factor, times the derivative of a Brownian motion. Right? And I imagine that not everybody here works on SDEs. So here's a nice picture. That took me a long while to get. Okay. So as I said, we have a very similar result also in this setting. I just also call it invariance. And it tells you that this measure that I define here, which is called nu, is invariant under the Langevin dynamics.
So I have a question. For this picture, what's your V?
So here I took the quadratic one with lambda equal to 1. But you would not be able to guess it from the picture. You would need more than one pass.
Right. Unless, oh, great. The square root of 2 is big.
Yeah. Right. Okay. So this is the result, and this measure looks very similar to what we had before, right? It has a normalization constant, it has an exponential, this time only with the potential energy and the Lebesgue measure. Right. So
this one is just a measure on R.
This one is just a measure on R, exactly. So the proof of this is now, maybe a little bit more involved, but not much. It essentially boils down to Ito's formula. So that's roughly the proof. So one thing that I want to mention here that maybe it goes a little bit further into what you just asked. We now have these two different measures. The Gibbs measure and this measure nu, this one is on R2 and this one is on R. But you should really view them as being the same measure. And the reason why that is because the Gibbs measure in Q and P is actually this measure nu here in Q and a Gaussian measure in P. And if you think of Gaussian measures as being kind of trivial, then it's the same up to trivialities. Right? So roughly speaking, you should view them as being the same. Right? If you understand this measure, you understand this measure because you understand Gaussians. And if you understand this measure, you understand the new measure because you just take a marginal. Right? So these are pretty much equivalent. Okay. One further comment that I should make here is why do we need this stochastic forcing? Right? Because after all, previously we started with the deterministic equation. Why now all of a sudden we have a stochastic forcing? Right? So we're interested in invariant measures. Right? But if you only had this term here, so if you only had this part, it would be a gradient flow. Right? But when you have gradient flows, you decrease something, you decrease the potential energy, and that's not good if you want to have something that's invariant. Right? So this kind of energy that is decreased by the system needs to be reinserted, and we do this by adding this kind of stochastic forcing. Okay, so this is roughly the end of my kind of slow-paced short introduction. I just want to summarize again what we saw. So what we saw is that once you have fixed the potential energy, you can associate with this three different objects. You can write on a Gibbs measure, you can write on a Langevin equation, and you can write on a Hamiltonian equation. And all of these are kind of determined, right? The one thing that you get to choose is the potential energy. Everything else falls into place.
Right. And just to make sure that I got it, the Gibbs measure associated to the Langevin equation is simply the marginal, like integrating out P.
Yeah.
At a certain Q, it's just integrating out P.
Yeah. Right. So they're really, you should just from now on, you should think of them as being the same, even though there's a slight kind of technicality.
You also have a free parameter there, right? The beta.
Yeah, right. Which I fixed already. Okay. Good. So let's move on. Let's move on to PDEs. So we now want to do this kind of.
If you added the beta, so this trick of integrating out P would be problematic, right? Because you need another.
No, it's fine. It's a different. I mean, you no longer have 1/2, but it's fine. It's just a different constant. You can also add another parameter in your potential energy, which is essentially the lambda that we just had. And there's another parameter that you can play with.
Yeah, I'm saying you need two parameters.
Yeah, you need two parameters.
You need the one, like beta is a coupling of the Hamiltonian, but now we have.
Yeah, you also have a coupling with
potential and the kinetic, each one.
Yeah. Right. Okay. So let's move on from ODEs to PDEs. So the very general question that I want to pose is, can we prove the invariance of the Gibbs measure for certain partial differential equations, right? At least from the way that I designed this appears to be quite natural. Now, this question sounds somewhat innocent, but at least in my opinion, turns out to be rather deep, right? In order to illustrate this a little better, let me just highlight 3 parts of this question. So first of all, this is a question about the Gibbs measure, right? Can we even construct this measure? Right, in the ODEs setting, this wasn't an issue because it was just a measure on a 2, you could just write it down. But in the PDE setting, it will now become a measure on an infinite dimensional function space, and these are much harder. Right? So we'll talk about this. The second question is, okay, this question concerns PDEs, but whenever I want to study a PDE, I need to at least know well-posedness, right? Because otherwise there's very little I can prove if I don't even know well-posedness. And in this particular setting, this will be some kind of probabilistic notion. Because we work with either random data or stochastic fossil, or both. And then once I've answered these 2 kind of more elementary questions in quotation marks, then I can address invariance, right? Then I can ask myself, can I actually prove invariance? Right? This can only be addressed once I have the measure and once I have some notion of the dynamics. Right? So, the question appears somewhat natural from the ODE setting, but let me motivate you just a little bit further. So there are different reasons here why you might care about this. So one of the motivations, which I mentioned about half a year ago in my short talk, is the Poincare recurrence theorem, or more generally results from dynamical systems. Right? So whenever you have an invariant measure, what you can get from these results is that you have some form of recurrence. So it tells you if you take a typical sample from a measure, then the nonlinear flow can do something, right? But eventually it has to return close to where you started, and this has to happen infinitely often. And it's a very interesting conclusion about the dynamic that you might want to know about. Right? The second motivation is maybe a little bit different in flavor, and it just concerns the propagation of randomness. Right? So what we're really asking here is, you have a PDE, you have some randomness in the initial data. What happens to this randomness as your nonlinear flow gets turned on, right? And this is very different from kind of the typical context of introductory probability theory classes, right? Because there you would look at sums of random variables, which are all linear operations. Here we really look at nonlinear operations, right? And this is kind of a question that to me seems quite natural in the context of both PD and probability theory, right? And maybe the last motivation I should mention here is quantum field theory, or more precisely Euclidean quantum field theories, because these kind of Gibbs measures that we will construct actually correspond to these quantum field theories. But if you want to know more about this, you should go ask Tom, because he's one of the world experts, and I'm definitely not. So that's roughly the motivation. Let's try to get maybe a little bit more specific. So what are the type of PDEs that we will now be studying? Right. So previously we had our position variable Q. We also had a momentum variable, but let's ignore that one for now. And we had a potential energy. And I will now just fix this parameter lambda to be 1. Right? So I'll now have this kind of quadratic quartic term. Right? Now these 2 objects will now be replaced by more complicated ones. Okay, my unknown will now be a function phi, which has a domain that is the d-dimensional flat torus. So here you can just think of a box with periodic boundary conditions, right? And it will map into a field K, which can either be R or could be C. These are the 2 fields that I allow. Right? And then the potential energy looks pretty much like what we had before, will also have a mixture of quadratic and quartic terms, but they will always come under an integral, right? So I have an integral of phi squared, the gradient of phi squared, and the function to the 4, right? That's the quartic term, right? So this looks like the natural PDE analog of what I had. So now, just like what we saw in the ODE setting, we can associate with this potential energy, at least at a formal level, several different objects. Okay, all of these objects are often called phi 4D models. And the reason why they're called phi 4D models is because there's a phi right here, there's a 4 upstairs, and there's a D downstairs. Right? So if you've seen this on archive or somewhere, that's where it comes from. So the first kind of object that one can consider here is the Gibbs measure. Right? At least formally, it's written down in the same fashion as what we did before. Right? We'll talk about this in more detail. But we can also look at all these different evolution equations. There's a Langevin dynamic, and this would lead you to a cubic stochastic heat equation. There's a real valued Hamiltonian dynamic, and this would lead you to the cubic wave equation. Now, there's one thing that I didn't quite discuss in the ODE setting, which is that there's also a complex valued Hamiltonian dynamic. So hopefully you believe me that if I allow this to be complex valued, there's kind of a different symplectic structure that I can choose, and it leads to a different Hamiltonian equation. And that one will be the cubic Schrödinger equation. Right? So I didn't write down any of these equations yet. We'll do so a little bit later in this talk. For now, I'm just kind of banking on the fact that these kind of keywords, heat, wave, and Schrödinger mean something to you.
Is there a reason you only have even exponents for your q's or phi's?
Right. So that's a very good question. So once you consider odd exponents, typically you lose coercivity. Right. So whereas q to the 4 has a lower bound, q to the 3 does not. So you can study these, but it's a somewhat different story.
Okay, thanks.
Sure. Okay, so there's a lot here that one can say. And this is really kind of a research direction that has been going on for about 6 decades. Right. So I'll now try in about 5 minutes to summarize 6 decades of research. And inevitably, there will be some omissions. Right? So I'll try to capture everything in this table here. The first column is the dimension, right, which is the dimension of my domain. Right? The second column is just the measure. So here I just want to know whether or not I can construct the measure. Right? And then the last 3 columns concern the different evolution equations. And here I want to know whether it's probabilistically well-posed and whether the measure is invariant under the dynamics. Right? So the questions that we previously discussed. So let's start filling this in. The first 3 results were obtained by this constructive quantum field theory community. The 2-dimensional case was addressed by Nelson in '66, and the 3-dimensional case was addressed by Glim and Jeffrey in '73. And this was really the crowning achievement of this constructive quantum field theory school. And these are all positive results, meaning that they can actually construct this measure, right? They can actually give a meaning to it. I unfortunately couldn't find a reference for this 1-dimensional setting, at least not from the time period. So I also asked Tom about it. It does not exist. I mean, you can now cite textbooks from the 90s, but it felt weird to kind of break with the historical order in that way. A little bit later, Eisenman proved what is called the marginal triviality of this measure in dimension 5 or higher. Right? So I don't really want to explain what marginal triviality means. What I want you to think of here is simply saying that, you cannot give a sensible meaning to this measure. That's roughly what it means.
Or if you do, it'll be Gaussian.
Or if you do, it will be Gaussian, right? Which to me would not be sensible. Right. So that's roughly what it means. I mean, certainly, Tom knows better about it than I do. So there's a very long story to it. But for this talk, I want you to think of it as saying, it doesn't exist in a sensible fashion. Right. So now, if you cannot really give a sensible meaning to this measure, you should also not study it.
Sorry,
yeah.
just to understand. It means that not sensible to the potential. The potential is fixed. So what do you mean?
Yeah. Let me shelve this question until we talk about the construction. Okay. Right. Because then I can explain it a little bit better.
Can I ask a similar question, which you probably also explained? What's the relation between the potential and the equation?
Right. So here you should think of the ODE setting, right? So once you have the potential energy, we could write on the Hamiltonian, and then there was a Hamiltonian evolution equation. And here in the PDE setting, it's exactly the same. You would have a Hamiltonian that comes from the potential energy, and you could write on an evolution equation. You would need one additional piece of information that I didn't tell you, which is the symplectic form, but that's fine.
Okay.
Right. So in R2, it's just the typical symplectic form dq dp. But in the PD setting, you have to actually write it down.
So the same V works for all of these.
The same V works for all of this.
Okay.
So that's really the point that connects all of them. Right. Okay, any more questions?
Because maybe just a comment that if you
Yes.
discretize your space, you have no trouble with any of this problem.
Yeah, if you discretize, all of this is fine. But then the question is what happens when
And
you
you try to remove the discretization.
and that will come in a few minutes. Good. So far we're here. This was the constructive quantum field theory school. This is now the point where PDE people get interested in this. Okay. So the heat case was first addressed by Iwata in '87. The wave case was addressed by Tsitkov in '94. And the Schwininger case was addressed by Bjoern, also in '94. And I think this is roughly the time when he started to come here. So I think he started here in '94. So, I'll put a pin in this for a second. Typically, you would think of these three questions as getting more difficult from left to right. So typically, the heat case is the easiest, the wave case is a little bit harder, and the Schwininger case is the hardest. Right? And this also fits here in this one-dimensional world. Right? However, if you're Bjoern, kind of none of this concerns you, and you can just do the most difficult one right away. Okay, so Bjoern did the Schwininger case right away. He also wrote down the wave case as a theorem in one of his lecture notes, but didn't prove it. He just kind of said it follows from the methods that I already have. I would imagine that he was also aware of the heat case, but as far as I know, he never wrote it down. And this was actually treated independently by Laplace and Debush, so I'll attribute it to them. Now, at this point in time, we're roughly, at the turn of the century, and we are about 4 decades into this, and everything that remains is rather difficult, right? So in 2013, there was this phenomenal work of Martin Heirer that came in the form of his regularity structures. So by now, it's kind of a very general theory with, many, many applications. But at least when it came out, the primary applications were, this kind of heat equation and the KBZ equation. Okay. Even more recently, there was work by Eisenman and Duminier-Papin, where they also proved the marginal triviality of the 544 measure. And similar as before, I want you to think of this as saying that the measure does not exist in any sensible fashion. So I'll also shelve all of the other questions in this row.
No, I would just say Heirer's work didn't really address the global existence, right?
Right. So that actually,
I'm being a little bit later.
Right. I'm being a little imprecise. There's an additional paper by Heirer and Matetsky that proves the invariance. And then there are other works by Hendrik Weber, for instance, where you obtain global bounds away from equilibrium. Right. So there's kind of a lot that you could mention here, but it would not fit in this one cell. Yeah. Okay. Very good. So now we are here, and this was the state of the art when I gave my show talk, right? So about half a year ago, this was the table that I showed you. Now we're able to fill in one more. So this is joint work with Andrea Namat, Yudain, Andrea Namat, and Heikki Nuhr. So there's only one cell remaining, and this is still open. Okay. So as Tom already realized, there's a lot that's missing here. So unfortunately, I don't have the time to go over everything that's missing. Let me just mention a few of the results that come from my own community, because otherwise I would just feel bad afterwards. Right? So you can zoom in into these kind of 4 cells, and there's kind of a lot that goes in between these. Right? So for instance, you could study quintic nonlinearities in dimension 2. You could study, maybe some modified nonlinearities in dimension 3, and so on. Right? So there's a lot of work here. There's more work by Bjoern. There's a very influential paper by Gubinelli, Kant, O. There's more work by my co-authors, Bringmann and Nuhr, and there's also kind of the bulk of my PhD thesis, and it all fits somewhere in between. But I thought that for this kind of general audience, I would just take this wider view, and I would not go into kind of the details of our literature. Okay, so here, let me now end this literature overview, and let me actually state our main result. And this is exactly the theorem that I just announced. So, and it tells you the following. Okay, so we consider the renormalized 3-dimensional cubic nonlinear wave equation. Okay, so what does it mean? On the left-hand side here, we have our wave solution, our phi wave, and I hit it with the wave operator. Right, so I have a second-order derivative in time, second-order derivative in space, and I have an additional massive term right here. Okay. On the right-hand side, I have a cubic nonlinearity, which is defocusing, which is why there's a minus. And I also have a renormalization, which I formally write as this kind of infinity times the solution, right? So, some of you know very well about these things, and some of you might hear this for the first time. Now, in this talk, I don't want to make this the main focus, right? So I'll say a little bit more about it later, but for the most part, I'll just ignore it. I just want you to be, not concerned about this. This is a very, standard thing that happens in all of these problems. Good. So this is a second order equation. As I said, it's in 3 dimensions, right? So 3-dimensional torus, and I have some initial position and an initial velocity, and these will be drawn eventually from the Gibbs measure. Right? So here's our theorem. With Udeng and they're now in a year. As of today, it's still in preparation, but it should be online rather shortly. So here's what it says. The cubic nonlinear wave equation is probabilistically well-posed with respect to the Gibbs measure. That means that I can take an initial data from this measure, and I can actually solve my equation, right? Globally in time. Furthermore, this Gibbs measure is invariant under the dynamics, meaning that if initially it's distributed like the Gibbs measure, and I solve it, and I look at time 1, it will still be distributed like the Gibbs measure, right? Exactly what it said in the ODEs setting. Right? Now, if you've never seen any one of these results, this may seem deceptively simple, right? Because after all, it's a result about a cubic wave equation. What could be easier, right? Like it's one of the most basic equations you could write down. But the reason why it's hard is because of the properties of the Gibbs measure. Right? So we'll go over this in more detail, but let me here just mention maybe 1 or 2 aspects that I find very convincing regarding kind of the difficulty of this problem. Right? So we have this kind of Gibbs measure, and up to this kind of technicality of having to take a product with a Gaussian that we discussed before, it is exactly the 543 measure. Right? So the 543 measure is this measure that appeared in our second column of the literature overview, and which was constructed by Glim and Jeffrey. So this measure has now been around for almost 5 decades. So we know, a few things about it. One thing that we know about it is that it's singular with respect to the Gaussian free field, right? So I didn't really tell you what the Gaussian free field is, but you should think of it as the, the PD analog of the 2-dimensional Gaussian measure that we saw before. Right?
This is a measure defined on what space?
On, let's say, a Sobolev space with a negative index. The next slide will be about the construction of this measure, and then we'll get a little bit more specific. Right, so you think of just functions, or more precisely distributions.
On what?
On T3. Yeah.
Sorry, is it a measure on regular distributions or also singular distributions?
What do you mean?
Like can they be written as functions?
No, so very good question. That's actually the third point here. So the regularity of these will be -1/2 minus. So it will not be a function, it will be a distribution with negative regularity. Okay, where was I? Okay, so we were here.
So in particular, you have to come up with what it means to take the cube of something.
Right. That's part of the reason why there's this kind of, we're looking infinity here. Right? So you can make sense of it, but you have to
subtract something.
Okay. So, right. So let's get back to this point. So I said that it's singular, right? So this is exactly the opposite of what we had in the ODE setting. Remember, in the ODE setting, I was able to write this down, and even if lambda was positive, it was always absolutely continuous with respect to the Gaussian measure. Right here, this does not happen. Right? It's singular, which means that the supports of these measures are completely different. And that's something that's specific to the 3-dimensional setting. In either dimension 1 or dimension 2, you can still construct these, but there it's absolutely continuous with respect to the Gaussian measure. This is really a 3-dimensional thing.
And does it live in a better regularity space?
Yeah, so the regularities depend on the dimension and will always be 1 minus dimension over 2. So dimension 1, it would be 1/2, then it would be 0, and then -1.
So in dimension 2, you can actually make sense of the cube of the function without going to the normalization?
Almost. I forget to mention this minus here. Right? So it's 0 minus. So in dimension 1, you can make sense of it. In dimension 2, you barely cannot. And in dimension 3, things get really tricky.
Okay. So you have to renormalize it in 2 dimensions too?
Yes. But less so than in 3 dimensions.
Much less. It's a log.
Yeah. Okay. So, right. So then I guess we already discussed this kind of third point here, namely that it has very low spatial regularity, And as we saw, for instance, from Camila's questions, that seems difficult, right? So that's the point here. Okay.
It's a stupid question, but when you're saying Gaussian free field,
yeah.
I guess you mean on T3?
Yeah.
And with what covariance?
The one coming from the Laplacian with an additional mass spectrum. So from this operator here. Okay, perfect. So this is the result. I know that I'm not being very precise so far. I'll not try to go over the proof, and then I'll try to be, as precise as I can be in a talk for a general audience. So that's the goal. Okay, so let's go over the proof. I think I'm doing okay on time. Let's first talk about the measure, right? So I'll talk a little bit about this. I'll talk a little bit about this, and this I'll mention briefly in the end, right? So the focus will be on the measure and on the local theory. So let's talk about the measure, right? So as we already discussed, it seems difficult to make sense of it, right? So at least formally, I want to write down something that looks like this, right? So this 543 measure should look like a normalization constant, an exponential factor that contains the potential energy, and a Lebesgue measure. So now the Lebesgue measure will be taken over the values of the function at every point in this torus, and then I'll take a product. Right. Okay. Problem with this is that it doesn't make any sense. Right? So there really is no infinite dimensional Lebesgue measure. If you think about it for a second, basically anything should have measure either 0 or infinity, and that's not very helpful. Right? So that's a big issue. Right? There's also a big issue here, as Camilo already pointed out, because I'm expected this to have regularity -1/2 minus, so all of this will just be infinite. Right? So that's another issue. The normalization constant will then, of course, also be infinite. So basically, none of these quantities make any sense. Right? So how can we still give kind of a rigorous meaning to this, despite all of these different problems? Right? So here's one approach that we could try to take. The first thing that we might want to start with, which is was already mentioned by Tom a little bit earlier, is that we take our three-dimensional torus and we replace it by a periodic lattice with lattice spacing epsilon. So then I have finitely many lattice points. Then at least the problem regarding the well-definedness of this kind of Lebesgue measure goes away, because it will now be a finite dimensional Lebesgue measure, and at least for a fixed epsilon, that's sensible. For a fixed epsilon, also the kind of argument of this exponential would be fine. Right? It will be some quantity that may blow up in epsilon. Okay, but then
you just discretize it, or
you just discretize it, right? So you replace the gradient by discrete gradient, the integral by sum, and put the correct powers of epsilon. Right. Okay, but then if this thing formally is infinite, you expect it to diverge as epsilon goes to 0. Right. So what do you do about all of these divergences? Right. Some of the divergences are not so serious. These are the ones coming from the quadratic terms. And morally speaking, they just kind of get absorbed into the normalization constant, right? So what happens is, you cannot take an infinite product of measures, but you can take an infinite product of probability measures, right? That's fine, right? But then there are other infinities, and these come from the quadratic term right here, and they are harder to deal with, right? What you need here are kind of low order terms with divergent constants. So you add kind of a quadratic term, but with a divergent constant, which kills off some of the infinities in your quadratic term. That's roughly what happens.
Can you explain again what's the
right?
What's the problem with 5 to the 4th against 5 to the 2?
Essentially because it's not Gaussian, right? So this Gaussian part here, you could factor into the individual Fourier modes, right? So write this in terms of the Fourier basis, for instance, then it's easiest to see, and then everything decouples, right? So if you normalize each of them individually, you can make sense of the product, it's fine, right? But the quadratic term would jumble up all of these different frequencies. So you cannot isolate them, which means you cannot understand it as a product of probability measures. And that is why this one is harder.
Like how we learned to integrate e to the minus x squared when we were kids.
Yeah.
Would it make your life easier if you were trying to discretize in Fourier space with Galerkin instead of?
Yeah. So in the paper, that's actually what we do. I just mentioned this one here because
this one is the historical one.
This one is the historical one, and this one I felt like was also conceptually maybe easier, but that might depend on your background.
Yeah. Okay. Yeah. I would have found easier like Galerkin.
No, I mean Fourier space is easier for us because we use frequency methods in our proof. we're good so far. I mean, all of this is, not at the detailed level. Hopefully, it makes sense at the level at which I'm trying to convey this. So there are issues with this here, right? So especially this kind of quadratic term, we add some terms to kill this. And this is called a renormalization, and this could be a whole nother story, right? I could give several talks about this, but that's not what this talk is about, right? So I'll now say, okay, there has to be something done here, but let's not focus on this, and then we'll try to take epsilon to 0. Right? But as you saw, actually taking this limit might be difficult, right? So first of all, in which space do you even take this limit? Well, some kind of negative solar space. But then actually doing this limit is difficult, but can be done. And this was this result that was obtained by Glim and Jeffrey in 73. Nowadays, there are also more modern proofs that use PDE methods, which I personally, given my background, find a little bit more accessible. For instance, there's a nice paper by Bjoern and Hoffmann-Over, and there's a nice paper by Monar and Weber. Right? And all of these tell you the same thing. They tell you that this lattice approximation converges to a well-defined limit, and this is what we call the 543 measure. So that's what we define.
To follow up on Camilla's question, do any of these guys they always use the lattice, or
Yes.
do they ever use
right. So Bjoern and Hoffmann-Over very clearly use the lattice because they're parabolic PD people. And Monar and Weber, they actually don't really do this limit. They just obtain uniform bounds, which you can then use to prove it. So there you would have to work a little.
It doesn't matter either one.
Yeah, it should be fine. Okay. So now we're here. Okay, now we have some kind of notion of what the measure should be. Right. What we now want to do is ask ourselves, do we have enough information about this measure to actually study our PDE? Right? Because that's what our goal is. So what we want to do is we want to take a sample of this measure, right? Sample phi, and we want to solve our wave equation. Right? So we want to find a solution phi wave which has the sample as its initial position. Right? There's also the initial velocity, but this one I'm ignoring because it's Gaussian. Right? So I'll focus on the initial position. Now, as we mentioned, there are different properties of these samples that make this rather challenging. Right? So one aspect is the spatial regularity of -1/2 minus. So unfortunately, I don't really have time to explain exactly where this number comes from. Right? As I said, it's 1 minus dimension over 2. Feel free to ask me about it after the talk or tomorrow, whatever. But here, it would take me a little bit too far astray. There's also the second difficulty, which is that when you write on the sample, the Fourier coefficients are probabilistically dependent. So this always happens when you have these kind of quadratic terms. But sometimes you don't have to deal with it. Right? In dimension 1 and 2, the measure is absolutely continuous with respect to the Gaussian measure, the Gaussian free field, and they don't have these dependencies. Right? So you just switch by absolute continuity, and then this problem goes away. Right? In 3 dimensions, the measure is singular, so you cannot avoid it. It's more intricately linked with your problem. And both of these things have been proven, so you can't avoid them. And I think it makes sense that these are difficulties, right? These are challenges that you have to address. So what can you do? Right? There's one thing that you can still hope for. Even though you have these 2 different problems or challenges, you can still hope that they can somehow be separated. You can hope that you can write your sample as a sum of 2 different pieces, one of which has maybe low regularity, but has very good probabilistic properties. And the other component, you expect to maybe have all of these probabilistic dependencies, but maybe it makes up for it by having better regularity.
Can you explain where the regularity coming from? Because the probabilistic dependence of the Fourier coefficients is clear from the fact that you don't have this decoupling. The phi 4 is going to give you. The regularity is also directly coming from the phi 4 term.
So since you already asked me about the Gaussian free field, let me give you a Gaussian free field reply. It's the same regularity as the Gaussian free field has. So the lowest regularity term in your sample, that's something that we'll see in a minute, actually corresponds to the Gaussian free field. And for the Gaussian free field, you can just compute it. Now I can show you the calculation afterwards. I do not want to start calculating right now. Right. So it's the same as for the Gaussian free field, right? So you write down the Gaussian free field with the covariance that is 1 minus L'Hochern, and then you do. Okay, so far so good. That was our hope. So how do we make this come true? Right? I wouldn't have given you false hope, right? I wouldn't have told you hope for this goes bad, right? So how do we make this true? right? So here we actually use the cubic stochastic heat equation, right? So this was exactly the equation that appeared in the third column of our literature overview, and it corresponds to the Langevin dynamics, right? So we look at this cubic heat equation right here. So on the left, I have a heat operator, right? On the right, I have a cubic linearity. I have this linear term that corresponds to renormalization, and I have this space-time white noise here. So this eta here will be a space-time white noise. It's kind of the PD analog of the derivative of the Brownian motion that we saw a little bit earlier. Okay, so this kind of equation remained a challenge for a very long time, but it is, what was addressed using this theory of Hyrer. This particular equation you can also address using this power-controlled framework by Gubinelli, Imkin, and Pekowski, which is kind of an alternative approach.
But these are all local time, right?
These are all local time, right? In our paper, actually, we only use the local time result. We do not.
You do not use it. I see.
I mean, we only need some result of what we measure, like the reconvergence, and then we use the local time result. We ended up not needing.
You're not using the local factor. Converges to the.
Yeah. I mean, we're using that statement for the measure, but not for the dynamics.
What is well-posedness?
So here it just means that, can you give a rigorous meaning to this equation? Again, kind of understood in the sense that you write down some kind of approximation and take the limit. Because this kind of space-time white noise here will be very, very rough. That's where the difficulty comes from.
Can you go back to the hope? Sorry, I just want.
Yes. So the hope is we want to write our sample as one low regularity component, but this one should have good probabilistic properties, and one other component that maybe has bad probabilistic properties, but make up for it by having high regularity. Right. So this was a very good transition to what I was now going to say, namely this idea, like how do we make this kind of hope, or how do we make it come true? Right. So we had our sample phi that we started with, and then we want to solve and then we are first going to solve our heat equation. So we're not going to solve the wave equation right away. We're first going to solve heat, and we're going to figure out this phi heat here, which has the sample as its initial data. And then we're going to solve the wave equation. We'll find a solution phi wave, or at least that's what we want to do. And the initial position of this phi wave here will not be the sample that I started with, but it will be the solution of the heat equation at time 1. So going back to Tom's question, it will actually be a small time, but I was trying to sweep this under the rug. So why is this legal? Right? So typically in a PDE setting, I'm not allowed to just change my initial data. It's typically given to me, and I'm not allowed to just change it if I don't like it. Right? The reason why this is allowed is because I already know that the Gibbs measure is invariant under the heat equation. So the law of this phi heat of 1 here will be exactly the same as the law of the sample that I started with. Right? So the perspective that you should take on this is the following. You should really view this cubic stochastic heat equation as a somewhat non-trivial change of coordinates. Right? So it's a change of coordinates that Martin Hyrer got a field tunnel for.
But does this mean that, like, realistically, if we didn't have this whole stochastic machinery and stuff like that, when I take something and propagate it with the heat equation, I get a better regularity?
You will not get better regularity because otherwise it would not be invariant.
Yeah, right. but does this still mean that somehow phi heat of 1 is a better object than phi heat of 0?
It is better because I know more about its random structure. Right. So it somehow, I mean, it's the same object in a sense, but it's written down using different sources of randomness. So it's a little bit complicated, right? So it's kind of written down in a different fashion, which I can then use. Right. So if I didn't have all this well-posedness theory, I would not know that I can write it in this way.
If you prove your result first, then could Hyrer do the same trick in reverse?
The well-posedness theory that you'll now get to for wave is somewhat harder than for heat. So I think in this way you would never do it. And it would also be hard because the wave dynamic is much more complicated. So the description that you will get, might be a good point to get to the next slide. So I will now describe to you what this phi heat of 1 is, and for the wave it will be much more complicated. So it would be much harder to use. Right. So okay. So having done this kind of change of coordinates, we now want to understand what phi heat of 1 is. Right? Because that will be our new initial data. Right. So here I will use these kind of dots that may look funny. And I'll explain where they come from in a second. Now I just want to explain what they are. Okay. So the first one, the blue one, this one turns out to be Gaussian. And it will actually just be the Gaussian free field. Right? And it will have spatial regularity -1/2 minus. right? So it has very low regularity, but very good probabilistic properties because it's Gaussian, right? But then there's the second one right here that we denote by the green dot. And this is a cubic Gaussian chaos. So its probabilistic properties will now be a little bit more complicated, but it will have better regularity. It will have regularity 1/2 minus. It's already much better. And then there's this red one right here. Here I'm not telling you much about its probabilistic properties because we don't really know that much about them, but it will have regularity 1 minus. This is more than good enough for our purposes. So I haven't explained yet what these dots are, but let me explain the colors. Right? So because of the regularities that you see here, you think of the blue one as a high frequency function. You think of the green one as a medium frequency function. You think of the red one as a low frequency function. And then these colors just correspond to the visible spectrum of light. And so it's kind of a typical type of notation that you often see in harmonic analysis. Now, in our paper, we call this the caloric initial data. And this terminology is motivated by earlier work of Terry Tao. So when Tao studied the waveforms equation, he has this idea that you could define a good gauge transformation for the waveforms equation by using the harmonic map heat flow. So he defined kind of a good gauge transformation for a hyperbolic equation by using a parabolic equation. This is very similar to what we're doing here, right? We're using a parabolic equation to help us in the analysis of a wave equation. Our setting is random, his is geometric, but other than that, it's somewhat similar of an idea.
Sorry, perhaps I missed it on the previous slide. What did you mean again by the change of coordinates?
That's really more of a heuristic, right? So in reality, really just writing it in terms of different sources of randomness. But heuristically, you can kind of view it as a change of coordinates.
But which coordinates to which coordinates?
That is a very good question. It would be the, you would write your sigma algebra in some sense as depending on a certain set of random variables, and then this set of random variables you switch. But, writing all of this down would be tricky.
Okay, thanks.
Sure. Okay, so far so good. So now we'll talk about the local theory.
So this means your initial data are always going to be created as looking at the heat equation at time 1.
Exactly, right. So exactly like this, right? So I think I'm doing kind of mediocre on time. I'll take about 5 to 10 more minutes if that's okay with people. Okay. Thank you. Yeah, this is not a Zoom talk. I mean, for some of you is. Otherwise, you could just, politely leave. Now it's, harder. So this is the equation that we've been studying for all of this talk. And now, with what we just discussed, we now take this caloric initial data. Right. So again, why is this difficult? Well, it's difficult because it all happens at a very low regularity. And we somehow have to make up for this. And we can only make up for this by using kind of the random structure of our evolution equation. So in order to use this random structure, we now make an ansatz. This ansatz will look like this. It consists of 7 different terms. And now you also see why this dot notation is useful, because I can build these kind of tree-looking things. Right? So I'll tell you, at least in very vague terms, what all of these objects are in the next 2 slides. Here, I just want to tell you, maybe the most basic piece of information that you would like to know about them, which is their regularity. So the first one right here, it will have spatial regularity -1/2 minus. So a little bit below 1/2, -1/2. So just what we had before. The next one here will already be a little bit better. It will have regularity just below 0. Then I have 4 more components that have regularity slightly below 1/2. And then I have 1 component that has regularity a little bit better than 1/2. Right, so there's a certain relation between these pluses and minuses, but that's not something that I want to discuss in this talk.
What about the randomness?
Right, so these things here will have a random structure that I can then use. And we'll talk about this when I define what they are.
Tree ones.
Yeah, it's the tree ones, also the axis, but to a lesser extent. And the Y will not have any random structure, at least none that I will use. So, so we have this table. So let me just highlight 2 aspects of this table for you. Right. One thing here is that there's a gap. Right. This is strictly bigger than this. And this is very important for our theory. This is what makes this a probabilistically subcritical problem. Our theory would not work if there were not a gap. The other thing that I want to highlight is this kind of threshold here, 1/2. Right? We're kind of dancing around this 1/2 here a little bit. There's something that is slightly below, something that's slightly above. But this threshold is very natural in our theory because it's the dual regularity of the lowest regularity object that I have. And so the lowest regularity is kind of -1/2. So dual regularity is very important because it determines whether or not I can multiply things without additional information. Okay, so let's talk a little bit about what all of these objects are. The first four are explicit stochastic objects. Okay, I'll tell you about the definition, but I don't expect you to remember it after this, right? What I really want you to take away is that they're explicit, meaning that I do not have to solve a fixed point argument for them. So the first one here looks a little bit like a lollipop. And if I hit this with the wave operator, I just get 0. Right? So this is a linear evolution, and the initial data is given by the blue data. So yeah, so this is why we use a line here, because it, it's a linear evolution. I think it makes a lot of sense to use a line to display a linear evolution. I should also say this is not our idea. This has been used quite heavily by the singular SPD community and also people before that. Then there are two cubic objects. There's this blue tree-looking thing right here. And if I hit this with a wave operator, I get the cube of the blue lollipop. So there are 3 dots right here because there are 3 dots on the right hand side. And that's cubic.
So that's where you have to define what you mean by taking the cube of that particular guy.
So it will not really be the cube, it will be this kind of renormalized.
This kind of renormalized. Yeah. Okay, right.
But just a comment for Tom, it will only be the wig order part. The other renormalization you don't need at this stage. So then you also have this kind of green lollipop. Right? So this again solves the linear equation, but we now have the green initial data. Right? And this is why I still call this cubic, right? Because the initial data itself is cubic, not the kind of PD aspect of it. Right? And then lastly, I have this quintic term right here, and I've hit this with the wave operator. I also get a quintic expression on the right hand side.
So is the philosophy essentially that you're taking the expansion of your cubic and taking all the terms that you can't possibly multiply, and for them you have to give a meaning to what the product is.
Right.
And the rest has enough regularity to actually multiply them as honest functions.
Except that it's not true. That is true for simpler problems. But here, this kind of procedure now stops. So this was a very good transition to the next slide. So I'm very happy with how I designed this. So you don't start this kind of Picard iteration. Right, as Camilo said. But now the problem is it stops gaining regularity at 1/2. Right? So then you're dead. And this is really what kind of the main idea of higher rank linearity and so on, where how to treat this difficulty that your iteration scheme is kind of stops gaining regularity. Right? So you now have these two components that we call pair-controlled components. It's this x1 and it's this x2. x1 will absorb all of the high-low-low interactions between a blue lollipop and 2 other components of your ansatz. And x2 will absorb all of the high-low interactions between a blue lollipop, another blue lollipop, and another component.
Can you clarify what you mean by high-low-low or high-low?
Right. So you write it at the trilinear product in frequency space, and the frequencies of the first one you assume to be of some kind of scale n, and then you assume that the frequencies of the other ones are much lower than the scale n.
Like what?
So you do a power product decomposition in frequency space. Typically, when you mostly encounter this, it's often bilinear. Here we use a trilinear one. So it's kind of, I'm not sure if this means something to you. It's a little bit paid decomposition in frequency space. We can talk about it over tea if you want to. Right. So what's the name of the game here? The name of the game is to find everything that will lead to contributions that have regularity below 1/2, right? Because that's not enough to multiply things. Now, just finding them and showing that they have regularity below 1/2 is not good enough because they need to have some kind of redeeming qualities, right? That someone need to make up for their poor regularity. So you need to find some kind of useful structure, but this pair product structure here is very useful. Now, the last component is this y right here. And the evolution equation for this certainly does not fit on this slide. Yeah.
So these stars, are they explicit in terms of the lollipops?
Yes. Yeah.
They're just complicated to write them down.
Well, there are a lot of terms, right? So there are a lot of options here for the list.
But they're explicit.
They're explicit, yes. We write down exactly what it is. So we now want to have this evolution equation for y. Right? We hit it with the wave operator, and then on the right-hand side, you essentially get everything, right? By which I mean, take any 3 of the 7 terms in your ansatz and multiply them, which is a lot, right? But then you have to still remove the ones that we already took care of, right? Some of them we've taken care of before, some of them we've taken care of here. So depending on how you count, you get about 80 different terms. Right. So what is the name of the game? Well, the name of the game here is you have to verify that you are indeed correct. Right. So you try to guess everything that has regularity below 1/2. Now you have to show that you were actually right. Okay. And this is really where the main part of the work is.
So you have to write out 87 different terms?
I mean, you make up some notation to unify some of them.
Seems like a lot.
And so when you say that you have some useful structure, it means that when you write it in the form of paraproduct, they have a better convergence because there's some cancellation?
Yes, there's some cancellation. So if you multiply, for instance, the blue layer code with x1, then the regularities do not add to something positive, so this might diverge, but there is some cancellation. So you can still define the product, even though the sum of the regularities is negative.
So like the sum of the lid of the tiny pieces, you're actually converging nicer than you would expect just by knowing that these guys have a certain regularity.
Yes.
That's what you're saying.
Yeah. Which, by the way, is not obvious. So the cancellation is somewhat integral. Okay. So as you can see from these kind of numbers that I claimed, there's kind of a lot of work. So here I'm just giving you a list of keywords. So one thing that I actually liked while working on this project is that we had to use tools from many, many different fields. Okay, so there's certainly some probability theory and some PDE. That's maybe not so surprising. But there's also some number theory or elementary geometry. There's a bit of combinatorics. There's a lot of harmonic analysis coming from these kind of high-load power products and so on. You know, there's SPD stuff. It's something that I very much enjoyed. Right? I'm not going to rattle down this kind of list here. Instead, what I now want to do is I just want to tell you 2 highlights, and then I'll end. Okay, so then I'll let you go. Right, so let me show you 2 highlights from this kind of local theory. The first highlight that I want to mention here is what we call heat wave objects. Okay, so recall we had this green caloric data, and that came from the cubic stochastic heat equation. Right? So when you write down what it is, which we can actually do explicitly, it contains heat propagators in a non-trivial fashion. Right, and then you look at what happens under the wave equation, and you have, for instance, products like this: blue, green, blue. Right? And now you have wave propagators. So you get both, right? Heat and wave propagators. And you somehow have to deal with objects that contain both of them. So for this purpose, we kind of developed a notation that is a little bit more detailed. This is what we call the longhand diagrams. So these are also called shorthand diagrams in our paper. And I certainly do not have to explain, do not have time to explain what these objects are. Right? There's only one thing that I want to highlight, like this white put them. There are these dotted arrows right here, and they correspond to the heat propagator. And there are these full arrows right here, and they correspond to the wave operator. And if I want to estimate them, I really have to understand what happens if I have a frequency, hit it with a heat propagator, then with a wave propagator, and so on. Right? This is roughly what happens here. Okay.
Solid is which propagator, and dashed is which?
Solid is wave, dashed is heat. And these kind of things are pairings, but that's not something that I discussed. So resonances. Okay, so last slide that I'll discuss here, my second person highlight. This is what we call the 1533 cancellation. And it is something that even today I find somewhat mysterious. So let n be kind of a large frequency truncation parameter, and let's truncate everything to frequency n. Okay, so a little bit like the lattice regularization that we discussed before. So then I can look at the square of this cubic object right here. And remember, this has regularity just a tiny bit below 0. So you might be worried about whether or not it can define the square. It may be defined, it may not be, right? Especially if you look at space. However, you're in trouble because this kind of square actually diverges as n goes to infinity in the sense of space-time distributions. So it diverges in an extremely weak topology. Now, one comment, this kind of divergence cannot be removed through these renormalizations that we briefly mentioned, because the renormalizations are dictated to you by the construction of the measure. Once you have constructed the measure, you already know what the renormalizations are supposed to be. You no longer get to change them. Okay, so this is a problem. This kind of divergence did not occur in the construction of the measure. Okay. So when we discovered this, we were distraught, at least for a couple of days.
That's pretty strange.
Yeah, it's pretty strange. And it means that you're in trouble, right? You now have a term that occurs on the right-hand side of your equation that diverges. Right? But we got lucky, right? Because there's this magic cancellation that we call the 1533 cancellation. So if you do not just take the square of this object, but you take 6 times the linear one times the quantic one, and then you add this kind of square, this actually has a well-defined limit as n goes to infinity. And turns out you can actually always group the terms in your nonlinearity together so that you only see this type of object and not the individual ones. Because there's a little bit of algebra. but that can be done.
And there must be some reason for that, right?
Yes, I would hope so. But I mean, we have one heuristic reason, and essentially boils down to this. We believe in the result. If this cancellation does not happen, you will be in trouble.
So this is almost I mean, the calculation that involves the grouping of these terms is sort of a finite calculation.
It is a finite but not short calculation.
Yeah, no, but I mean to say that you don't need to understand some sort of deeper algebraic reason in order to do the grouping.
No, I can very much prove this without really understanding the concept.
Yeah, I see what you mean.
But I would hope to remedy this at some point. Right. Okay, so this is everything I want to say about the local theory. I had like one slide about the global theory, but by now there's kind of a paradigm.
Is that the only occurrence of a phenomenon like this, or do you have others? So the others can be treated like
there's one more occurrence, which is when you multiply this kind of blue one with the x1, but that is something that was observed before, and there's also a much shorter calculation, so it was kind of less mysterious.
What's 1533?
Very good. Thank you for this catch. So we call it 1533 because this is a first order object, a fifth order object, and a third order. And
Okay.
So it would be maybe better 15 plus 33.
I mean, we needed a terminology that distinguished it from the other cancellation, the one with linear and x1. Because we can't always see, cancellation. They have to get names. Yeah. So I had one slide on the global theory, and it involves Bourgain's globalization argument, but this is by now kind of a standard paradigm. So I'll skip that one, and I'll thank you for your attention.
Well, thank you very much for a very nice talk, very clear talk. Of course, we don't understand all the details, but we got a good feel for what you did. How long is the paper going to be?
About 180 pages.
Okay. So when are you doing Schrödinger at this point?
Well, we'll see. Not this year, maybe.
Well, next year.
Yeah, I mean, you hired me for 3 years.
Yes, exactly.
Well, are there any questions or comments? Yeah, see some.
I have a short comment, actually. If you're looking into cancellations, you might try looking into renormalization theory application to mathematical quantum field theory. I know there's been a lot of work in that direction. Maybe that could help you shed some light as well, or like get a new perspective.
Yeah, thank you. I mean, some of it I think already enters when you talk about the construction of the measure, but certainly there could be more that could be helpful. Yeah, maybe I have to pin down one of the physicists here at lunch.
So yeah, I don't know what they think about this particular type of evolution, but so you could do this if your fields were complex, or
yeah, I don't think that makes a huge difference. Yeah, like vector value is fine.
Vector value is fine.
Not claiming that I checked every detail, but
Yeah,
I don't see
there shouldn't be anything. That's
yeah.
So I have a question. So you have the second derivative in time.
Yeah.
What happens if you just add a first derivative in time? Does that?
Oh, I mean, depending on how you do it, you either get something like heat, right? Or you get another dispersive equation, but then you should really add an I or something, right? And then you get Schrödinger. Right? So you could get heat, you could get backwards heats, which you should avoid.
I'm saying keep the second derivative, but add also a first derivative.
Add another first derivative. That typically doesn't make much difference because that's kind of a damping term. But kind of most of the difficulties here are local, and locally in time, the damping really doesn't make a huge difference. So you would no longer have invariance unless you also add some kind of stochastic forcing.
Any more comments or questions? Okay, thanks very much.
Thank you so much.